So good morning, everybody. This is the sixth session of What Geochemistry Tells Us. Today we have two invited speakers, Sabin Zahirovic. We'll start. He's a researcher, professor, how should I put it, Sabin?
Lecturer.
Scientist, let's say it, working on modeling in tectonic with the tectonics, and he will present a short talk. So Sabin, it's all yours.
Okay, fantastic. Let me share my screen and get everything going. Good morning, everyone. Thank you so much for coming along. And Arthur and team, thank you so much for the invitation. I really appreciate to be here, and it's a great honor. To all of you, greetings from Sydney, Australia. It's the afternoon here. It's the morning over there. Hopefully you have your coffee ready. As Arthur said, my expertise is in tectonics, so my geochemistry is awful, to say the least. So, but I've tried to make this talk as relevant as possible. So today I'll talk about how we use our numerical plate tectonic reconstruction models to give us some insights about the sinks, carbon sinks, and also the cycling and exchange of carbon between different reservoirs on Earth, whether it's the mantle, the lithosphere, and so on. And a lot of this work was done through the support of the Alfred Sloan Foundation, the Deep Carbon Observatory. You see this C, about 10% of it is cut off, and the idea is that about 90% of the planet's carbon is in the deep Earth, locked in the mantle. So you can imagine that this very thin layer of the atmosphere and hydrosphere is quite susceptible to perturbations in the carbon cycle, through volcanism and tectonic activity. So hopefully I'll be able to give you some examples of that. Of course, none of this is possible without a great team of people shown here. This is all the people at the Sydney side. And of course, we've worked with wonderful people like Sasha Brunner, who will be talking a little bit later as collaborators. But this is the team at Sydney of academics, software developers, and of course, the engine of the whole process, which are talented students. So if we just step back and think about the planetary carbon cycles, we think of Earth as this beautiful blue planet with great habitability. And we compare other neighboring terrestrial planets, which are kind of in the Goldilocks orbit, so this favorable orbit around the sun. And if we compare the carbon cycles, well, we think Venus probably still is geologically active with volcanism, but it seems to have this one-way carbon valve of volcanism and emitting greenhouse gases, and you have this runaway greenhouse effect, making the surface temperatures of about 450 degrees Celsius. And Mars also seems to have had mantle convection, perhaps a weak carbon valve. We don't really know all that much because a lot of the atmosphere has been stripped off. And one of the really unique aspects of Earth is that it has a two-way carbon valve. We have emissions of greenhouse gases from tectonics and volcanism, of course, but we also have mechanisms to return that carbon into rocks, into sediments, and even back into the deep Earth. So, clearly Earth is a very special place. And today I hope to cover how this tectonics and mantle convection process has altered carbon cycling and other geochemical cycling on Earth, with just a few examples, very rudimentary basic stuff. But one of the things I wanted to point out today, I'll be discussing the role of submarine and subaerial volcanism and volcanic degassing. I have a lot of questions for you guys, which is related to whether the degassing happens in submarine or subaerial environments. So that's one thing I'd love to hear from you. But clearly these processes have changed ocean water chemistry and of course atmospheric greenhouse gas compositions, concentrations. This is just a schematic of the atmospheric compositions through time, of course, they've changed. Oxygen, of course, free oxygen is because of the biosphere, but a lot of the evolution and the balance between the different components has been driven by tectonics and geology. And of course, these processes have implications for planetary habitability, natural variations in climate, and the technical aspect of those biogeochemical cycles. And of course, in the most extreme cases on Earth, we've never really had a runaway permanent ice house or greenhouse, but we've come close in some ways. This is the snowball episodes where the ice sheets seem to have grown and met at the poles, with the feedbacks related to the albedo being, energy being reflected back on Earth. But it seems that we broke through the ice thanks to the volcanism and the greenhouse gases that were emitted as a result, of course, through tectonics. And then in terms of greenhouse climate states, here is just an example of Antarctica being on the South Pole, but having lots of these temperate rainforests. We have petrified fossilized wood from Antarctica, suggesting quite mild conditions. Of course, the glaciations on Antarctica only started about 35 million years ago. I don't want to dwell on this, but this is just some example. This is from Ben Mills et al. 2018. Just a nice little schematic of the carbon cycle, the strontium cycle, and its relation to tectonics, geology, erosion weathering, and so on. So hopefully you get an idea that the tectonic processes clearly play an important role. And in the Deep Carbon Observatory, since about 2009, the aim has been to try to quantify the carbon fluxes and also the size of the reservoirs, whether they're in the mantle, lithosphere, or the crust. So there's been some really interesting work, but this schematic at least gives you an idea of some of the sources of carbon in this case, whether it's mid-ocean ridge volcanism, or arc volcanism, or intraplate volcanism, and so on, as well as the consumption and return of this material into the Earth's interior. Okay, so we looked at this process from a context of plate tectonics through time. We at Sydney University developed this tool called G-Plates. It's a deep time geographic information system. It's free, open source. You can install it on your Mac, Linux, and Windows. But it allows us to undo seafloor spreading, get back to Pangea, and then also look at the evolution of the continents and the plates. And one of the greatest innovations came from this work from Mike Ernest and others, included me back in 2012, of building plate boundaries or evolving plate boundaries. So if this is a plate, you have individual boundaries that can move independently, but G-Plates resolves the topology of that plate, and we can use it to sample the velocities of these plates. And so the big advance was that we moved from this idea, the simplistic idea that continents could move around on their own, to this more complex and interesting true plate tectonics reconstructions that consider the plate itself, the plate boundaries, and so on. And so this allowed us to create models like this. So I'm going to just pause this animation, and you can see the continents. They're just colored by the age of the lithosphere. So you have these cratons in red, Proterozoic shields in orange, and then Phanerozoic in yellow and gray. But importantly, what you should focus on is just these thick lines. The black lines are mid-ocean ridges and transforms, and the pink teethed line indicates subduction zones. Okay, and then because we create these topologies in G-plates, we can sample the plate velocities across the entire plate, and as they evolve, We can track, what is the convergence rate in any part of the subduction zone? What's the angle of convergence? How does it evolve through time? And so on. So we can interrogate these models, and it's quite powerful. So if you wanted to download and use gplates, you can just go to gplates.org. A lot of documentation and a big user community. And so one of the first things when we started our involvement with the Deep Carbon Observatory in 2015 was to look at, well, there's been this idea from Van der Meer et al. In 2012, and there's other papers that approximate subduction zone lengths to the slab flux through time. And they did a really interesting study of looking at tomography depth slices where they identified these blue regions, cold regions related to subducted slabs. And they mapped out where they thought these subduction zones were, and therefore the arcs were. And so they came up with this relationship, essentially that you could estimate slab flux based on the depth of this subducted material, and you can assume how fast it sinks, and therefore infer the slab flux and therefore the carbon flux. And so we did something similar, but just from the plate tectonic reconstructions, we just measured the length of subduction zones through time. And so this is just the global subduction zone length from 200 million years, so about Pangea time all the way to the present. And you see there's some, peaks and troughs and so on. And one thing that puzzled me when we did this was I was aware that in the early Cretaceous, we had a warm, greenhouse climate, but this analysis didn't really support that. It suggests that if it was driven by arc volcanism, then perhaps it was warm in the late Cretaceous. So it wasn't really conclusive. We didn't really know what this meant until we had the great work of Simon Williams, first of all, who created the workflow, John Cannon, who also created the workflow, and the very talented Madison East, who was a student at the time, looking at these models in greater detail in terms of trying to capture the convergence rates along the subduction zones. And so the deeper the blue, the more plate is being subducted, the higher trench normal convergence that you have. And so you can see through time, this is time here. You can see that East Asia, there's high rates of convergence at this time. It's very high here in the early Cretaceous, and then it wanes a little bit and changes through time. But yeah, you can see there's another speed up here from the Izanagi plate subduction, and so on. And so what Madison could at least look at was to see, first of all, is there a relationship? Can we actually say that the flux of material being subducted, the carbonate sediments and so on, which are then remobilized in the arc volcanism, can we say that the subduction zone lengths are a proxy for how much stuff is actually subducting? And the resounding answer was actually just no. You really can't. The relationship is not anywhere near some kind of linear relationship, and that's because the convergence rates, as you saw, change through time. They change along the one subduction system. So when we looked at this, when Madison looked at this, this is time again from about 200 to present. This was the slab flux that took into account the convergence rates along the subduction zones. Okay, this is kilometers cubed per year. We also looked at the subducting plate area. That gives us some idea of how much sediment is going down, and it was a very similar trend. But it was very interesting because the peak was now in the early Cretaceous. Okay, it was you can see from this the subduction zone lengths, they peak in the late Cretaceous, but this peaks now at closer to like 135 million years ago. So that was really interesting. It was starting to make a little bit more sense in terms of, okay, if you're subducting more plate, you're subducting more of the carbonate sediments that are being trapped on the seafloor, and you're remobilizing them and releasing them in the arc volcanism. And you could explain some of the warmth that we were seeing in the Cretaceous. And the other really interesting thing was when we plotted also the large igneous province eruptions through time, there seemed to be this real interesting increase, a spike in large igneous province activity just after the peak in the slab flux into the mantle. And then following that, there seems to be some other expressions in the mantle that, you had lots of subduction, and then you had this process, this Darwin rise, these mantle superswells seem to have become stronger. So that was just fascinating when we had a look at it. It was it was really just mind-blowing. But the idea was that during that early Cretaceous period, or time frame, there was a lot of subduction, increased convergence rates, and of course, the more material you subduct, the more lower mantle material you displace, and we think that has strengthened the superswells and triggered the ascent of some of these massive large igneous provinces, so that we see in the Pacific, for example. It also matches some independent estimates of arc volcanism in terms of magma flare-ups in this time frame in the Cretaceous. So that was another thing that was quite interesting. And the general idea is essentially what you're seeing here. This is a mantle convection model that I run in SitcomS with imposed plate velocities and subduction locations. And what you see is, as the more slabs that you subduct, you actually sweep up this hotter return flow, and you trigger more of these mantle plume eruptions. So that's the idea. Now, the question I have for geochemists, for all of you, is, we know that the Siberian traps, when they erupted 251 million years ago, triggered the worst mass extinction, right? The CO2 that was liberated by the Siberian traps seems to be enormous. And it was from the mantle, but it was also from the crust and the lithosphere, the decarbonization of the limestones and the coal that were buried. And so I understand that the oceanic large igneous provinces have less carbon material to remobilize from the crust. So this is the Ontong, Java, Manahiki, Hikurangi super large igneous province. I mean, this is probably the closest thing that I've seen of a super plume on Earth, but it erupted in the oceans, right? And so despite being huge in extent, we have some ocean anoxic events at that time, but not there's no tipping points associated with it, in terms of mass extinctions and so on. Okay, so that's something I'm curious to hear about, is like, well, what happens to that carbon that's released by these mantle plumes that erupt in a submarine setting? Does it get a lot of it taken up by the seawater and the sediments, and only a little bit ends up in the atmosphere? But then also CAMP, the Central Atlantic Magmatic Province, 200 million years ago, is associated with a warm period, but again, not a mass extinction. So what's similar and what's different between these things? I think the geochemistry could potentially tell us a lot. And this is just a timeline. Here is in these gray bars, are the ocean anoxic events in the Cretaceous. So here's the Aptian one at 120. It's fairly short-lived. and then in the albion and so on. So that, I mean, this is more of a question for the audience that we can discuss. And of course, I just discussed the role of volcanism and the input of carbon into the atmosphere. But we also, of course, on Earth have this silicate weathering where, well, as the planet warms, the hydrological cycle intensifies, you have more rain, and that rain tends to pick up more CO2 from the atmosphere that's dissolved to make a very weak carbonic acid. That carbonic acid interacts with the elevated regions, mountain ranges, particularly active ones, other silicate rocks, and it flushes out carbonate, bicarbonate ions into the oceans. They tend to be picked up by calcifying organisms that make shells and so on. And that carbon that started in the atmosphere gets trapped as sediment, or thick layers of sediments on the seafloor. And it can take tens of millions of years before it returned into the subduction system. So, we have these mechanisms, of releasing CO2 and then also sequestering it. And that silicate weathering is, of course, also dependent on the where you have precipitation, where you have rain. And this is a plate reconstruction from Chris Cotees and work from Paul Valdez, who have done climate simulations. And what you can see in dark blue is where you have lots of rain. This is the near equatorial humid belt. And you can see that the arrangement of the continents, here's Pangea, and it will break up again. The arrangement of the continents really does modulate the shape and the location of this near equatorial humid belt through time, right? But it gives you an idea of where that weathering is. And so we did a very simple study with, it was simple but very interesting and also very powerful. Again, very talented student, Louis Johansson, who looked at the eruption of the large igneous provinces. You see these dark gray polygons, their eruption, their area of eruption, and also how much of that area is in the near equatorial humid belt in terms of the erosion. So there's Camp. Okay, you can see it erupts in near equatorial latitudes and it gets weathered clearly, right? What we don't really know is what happens to the marine lips. That's, again, a really interesting thing. Hopefully that maybe some of you have some insights. But we can, so that allows us to interrogate these G-plates plate reconstructions. We can look at the area of the large igneous provinces in the humid zone, and we can say, well, within 5 degrees of the equator, 10 degrees, or 15 degrees of the equator. That's these 3 colored curves. You can see Camp really is the dominant one, say 200 million years ago. Then we have the Deccan traps, the Arabian Afar lip, and so on. So we can track those and create these time series. And we can then compare the time series to the atmospheric CO2 from, say, Foster et al. 2017. And, I could say, well, there's an eruption, there's the eruption of Camp, and that explains this whole CO2, atmospheric CO2 perturbation. But, this is that's a very biased observation. We geologists like to look for patterns, but we try to actually do it in a more objective way without getting involved. We try to do it numerically. And so we use these cross wavelet transforms. I don't really want to bore you with the technical details here, but it essentially allows us to compare 2 time series, find the common power and therefore the correlation between the 2 time series, but also importantly tell us which signal leads one another, right? If you have lots of large igneous province eruptions, you expect that the CO2 should go up slightly, later. And so we could, this top panel here is in terms of the CO2 drawdown, and we found that that weathering in the near equatorial humid belt was very important for reducing CO2 in the atmosphere, probably between 260 and 160 million years ago, and then since about 100 million years ago. So that's what these analyses indicate. In terms of releasing CO2 from mantle plumes, it looks like it was quite important during Amy-Shan and the Siberian traps, but then more recently, the Deccan traps from 90 to 50 MA, but also all the other lips during that time. Okay, so it allowed us to at least quantitatively and objectively compare the time series. And so one of the outcomes of all this work was led by Kevin Wong, again, another very talented a student based over in Cambridge and then Leeds. And he compiled the best estimates that we had of the carbon fluxes from the different tectonic settings. Okay, so that gives you some idea. We can come back to this later. And more recently, we've been working with the paleogeography. You can see these are the mountains here in orange. We can track those through time. We can track the large igneous provinces. We even have now deforming plate reconstructions where we can look at, the contraction of continental crust and lithosphere and so on. So we've been able to expand these models more recently. This is just an example. These are the mountain ranges in the near equatorial humid belts. Again, during that Pangea assembly time, you can see there's lots of mountains and perhaps there was a lot of silicate weathering. Perhaps that explains the ice house episodes that we had. Perhaps there were other things going on. And of course, in the last 50 million years where we had the Tethyan mountains, we had an ice house. I mean, I probably shortened this ice house to about 34 million years where we have Antarctic glaciations, permanent ice sheets on Antarctica. So, there seems to be some relationship here with the ice houses. We've also been looking at ophiolites and particularly ophiolite abduction through time. And there seems to be a lot of ophiolite abduction in the last 30 million years thereabouts related to Southeast Asia, Sunderland. But, again, one of the things that you're seeing here is that, I'm just talking about ophiolites and mountains and individual components. And there's going to be a lot more work to actually try to combine it all together and get a holistic picture. Something that I wanted to talk about as well today is subduction and the interaction with carbonate platforms or any carbon-rich rocks in the crust. Mount Etna is a good example. It releases a lot of CO2 because it's interacting with a lot of crustal carbonate. And I wanted to talk about this today because actually today, I know it's April the 1st, but probably not a good omen to start a new project. But I start a new project that's looking at carbonate platforms in deep time. But this was work done by Emily Mason back in 2017, a very prominent science paper that was highlighting, this is much more relevant to all of you and you know more about it than I do, but the idea that the carbon isotopes from many of these volcanoes around the world seem to be linked with how much limestone or carbonate material is interacting with the magma and the plumbing system. And so we looked at this as well with the amazing Jody Parle and Sam Doss and looked at carbonate platforms through time from Wolfgang Kiesling's compilations. And because we have the plate tectonic reconstructions, we can actually look through time, this is, here's Pangaea, and we can look at the subduction zones, and we can see, well, are the carbonate platforms, these green polygons, on the overriding plate, or are they, where are they, right? Well, these ones would not be interacting with the subduction zones. I mean, they may be interacting with the rifts, but you can see the Tethyan system is much more important. So we could, again, track these carbonate platforms through time. One of the things we don't know is how thick these carbonate platforms were and how much carbon they had in them. But this was a very simplistic first step. And again, we use these cross-wavelet transforms, and you don't need to understand what's shown here, except that these were the results. The first thing was that the interaction of these massive carbonate platforms and subduction zones seems to be very variable through time, depending on the tectonic setting, but it seemed to be quite important from 350 to 300 million years ago during Pangaea assembly, and then during this latest Cretaceous, earliest Cenozoic, during the Tethyan subduction, where we could show that the subduction zone length interaction with the carbonate platforms are correlated and in phase, and also lead the CO2 signal. So that's the power of these objective numerical observations. Of course, there's lots of uncertainties in the plate reconstructions. There's uncertainties of how big these polygons, carbonate platforms were, but it's an interesting first step. And I'm not really going to dwell on this, but this is just a summary of the different components of the tectonic carbon cycle, the sources and sinks. So I've got anything that's a green plus, is probably an obvious release of carbon. And with I don't want to preempt and all the great things that Sasha will say, but I do have to say this is very interesting. How much do continental rifts actually contribute to the global carbon cycle? And the answer will be surprising, and I'm looking forward to Sasha's talk. But you see there's other places that have these, red minus signs that seem to be consuming carbon from the atmosphere, and some other places that are much more mixed. For example, mountains, the metamorphic degassing will release CO2, but the weathering of silicate rocks will consume CO2 from the atmosphere. So it's an interesting and complex problem, as you can see. We're trying to now look at the weathering of all of this in a regional and global setting. We're also trying to look at carbonate platform growth in these landscape evolution models. These are developed by Tristan Saul. It's a software called Badlands. But you can see here the evolution of landscapes of Australia, the erosion, deposition of sediments. We can track sea level change. We can impose tectonics. You can see there's a huge mountain range that uplifts and then subsides. And we can also combine it with a mantle convection in terms of the dynamic topography. So that's going to be quite interesting. This is just another example of this work from Tristan that's looking at the growth of reefs, particularly the Great Barrier Reef on Australia's northeast coast. And you can see that about 8,000 years ago, sea levels rise on the continental shelf since the last glacial maximum. You switch on the growth or the renewed growth of the Great Barrier Reef. And so that's something that I'll be working more on the next few years. And this the whole idea is to try to build these models that incorporate plate tectonics and mantle convection and also the climate and so on. Building this digital twin of our planet through time, but none of this is possible without the incredible work of people, like Arthur, who are essentially risking their lives and sampling rocks from volcanoes and other precarious locations. So thank you, Arthur, and everyone, particularly our friends in geochemistry who do that. But the big challenge is to incorporate the data and interrogate the models, make sure that it makes sense. So I'm keen to hear what everyone thinks. So to conclude, I just wanted to showcase that, well, we've built this community infrastructure, the software, we release the software G plates, we release the plate reconstruction models and many of the data, well, the databases we publish and release. So you can double check, you can build on that. There's a lot of infrastructure that we provide. In terms of the conclusions from my talk, that subduction arc lengths are probably not a great proxy for the slab flux in terms of how much carbon is going into the subduction system and how much is released at arc volcanism. Tectonic exchanges of carbon change through time. They seem to be punctuated by sharp perturbations during these major events, whether it's large igneous provinces erupting or, say, subduction zones initiating or being shut down through continental collisions. Numerical models are great, but we really need to be careful how we interrogate them in that we link them to very good quality data. So, for example, when we just looked at the subduction zone lengths from G plates, you get a nice output, but what does it actually mean? One has to actually look back at the geological data and the record to try to make sense of it. In the near future, and this is work already underway, is to look at these global landscape evolution models, silicate weathering, that consider ophiolites, mountains, and so on, but also incorporate carbonate platform growth, because that gives us a better idea, perhaps, of the thicknesses of the carbonate platforms. Now, of course, in the ideal world, we would have all of the data from the oil and gas companies that tell us the thicknesses of some of these things. That probably won't happen. I hope it will happen at some stage. But yeah, so we have to trawl through the public literature and then, do these models and try to make sense of it. So that's all I have for today. Thank you for your time, and I'm happy to take any questions.
Thanks, Sabin. Any questions for Sabin? Or comments? Don't be shy.
Can I start?
Right.
Is that okay?
Yes.
Go for it.
I was interested by this East 2019 paper with the super swell being triggered by subduction flux. Maybe you can go to that. Yeah, this one.
Yeah.
So I was wondering, so first thing is that when you have more subduction, then the volume of the Earth should be conserved. So anything that is a direct effect of having a faster subduction rate would be immediate. There wouldn't be any delay. So you would get an immediate response of the surface somewhere. And the second part of the question is, when you were going to say, oh no, I let you say it. Yeah.
Oh, no, I mean, that's absolutely correct, right? We have to conserve volume. I think that the point that I should have made is that we think that there's a slight lag in the sense that there's some ponding of the slab material in the upper mantle, and then it enters the lower mantle, probably as mantle slab avalanches, which we have seen in numerical models. So that's where we think the lag comes from. But your question is still relevant. Like, well, then what happens to the asthenosphere during this time, right? If you have so much slab accumulating in the upper mantle. So, perhaps we need to think more broadly in terms of, the hotspots and mantle plumes, and hotspots sourced from the asthenosphere maybe were elevated during that time. I know that in the Pacific we had oh God, I can't remember the non-age progressive, the Line Island Mountains or whatever. Anyway, but there is some evidence of intraplate volcanism that is not age progressive. So that could explain that maybe.
Another way would be that you also have the increase of mid-ocean ridges and of rifts during that time in the Cretaceous. So material might just be transferred in the asthenosphere coming back.
Yeah, yeah. And I mean, you know, like I said, this is just looking at the subduction, you know, component of these models. It doesn't capture the whole carbon cycle, of course. One thing is that, you know, there is an increase, there's an interesting uptick in large igneous provinces at this time. But of course, this is during this time, we don't have a lot of preserved seafloor either. So I don't really know, apart from the fact that at least with the numerical models, you know, as we just said, that, yeah, the more that you subduct, well, the more material you're going to displace and trigger the Rayleigh-Taylor instabilities, which are the plumes. So simplistically, it does make some sense.
But sorry to continue on this, but then it would be taking 100 million years from the subduction flux at the surface to reach the core mantle boundary and to push the plumes upwards. And this is not your scale here, 100 million years, it's faster.
Yeah, exactly, right. It's faster, but when we looked at Southeast Asia in detail with Mike Gurnis a couple of years ago, the Java Sunda subduction system initiated at about 60 million years ago. And it seems that the slab avalanche started to occur from about 30 million years ago, right? So within 30 million years, it seems like it was feeling the lower mantle was feeling the effects, you know, more strongly of the avalanche. And we could link that back to, you know, the slab, the Sunda slab at the present day, but we could also link it to the geological observations, the dynamic subsidence, and also the intraplate compression, the basin inversions that get triggered when you have a trench advance during a slab avalanche. So I wouldn't say that it's a full 100 million years, but I agree with you that the lag is probably closer to, you know, 20, 30 million years based on the models that I've seen, at least.
Okay, thanks.
Yeah, thanks, Sasha. Any other questions? Criticisms?
I have a comment.
Sure.
So when you were presenting with the lips, so example in the oceanic one, if it's a huge, large igneous province, it's based on the models, it's the CO2 is less going to the atmosphere. And one of your question was, why is this?
Yeah.
So I think in the geochemical point of view, so in my opinion, it depends also the amount of seawater or oceanic water that, because we know that, let's say, a part of that CO2 can be dissolved in the water, so it remains in the oceanic water. It won't be released. I'm thinking on this is if you see how somewhere or somehow how much oceanic water was above it, and to see, okay, if this is a large igneous province, this would be the amount of CO2 released, how much was retained in the oceanic water. Because it's in water, if you take normal water, if it's an acidic one, let's say pH, automatic, or the carbon is released. However, if it's more neutral or more alkalic, let's say pH 8, a big chunk of the CO2 is retained. So it can reprecipitate to carbonate, or it's just inside the water, and that's it. And you won't see this high amount of release. So maybe this could be a simple explanation for this model.
Yeah, I mean, that makes a lot of sense, right? Because this ocean crust, I mean, you can see that there is a reasonably fast spreading seafloor system. So sea levels were, well, the column of seawater was probably close to, I don't know, 3 kilometers thereabouts here. So there was a significant, amount of seawater that, I mean, if we think of the ocean circulation, it's a fairly efficient mixing on, well, geological timescales, it would be fairly efficient in mixing. And we do have the anoxic events. So, yeah, I mean, it's just a very interesting problem. I mean, it also is somewhat linked to the Central Atlantic magmatic province that was also mainly subaerial, but, over a very large area. And maybe was it just erupting over a longer period of time, or did it not remobilize a lot of carbon? I mean, I just maybe it didn't reach the tipping points of, say, the end Permian mass extinction event. So. Okay, great. Thank you, Arthur.
Thank you, Sabin. So any comments or questions for Sabin?
I think we should take it.
I would be interested in when you showed this Johansson study with the lip polygons that were crossing the humid belt. Your polygons are representative of present day, so they don't show how much the lip actually was, and some of them might have been much, much bigger.
Yeah,
so I
exactly.
was how much this could change the picture.
Yeah, exactly. So yeah, these are the eroded present day extents, particularly on the continents. And so just in terms of the area of weathering, that's very important. You also saw that from the Johansson paper, we did a very simplistic a comparison to just a very narrow band near the equator. And I mean, we're doing it. We've been doing it now with the climate output models, but it still doesn't answer your question of, what was the original extent of the Central Atlantic magmatic province. So that's one problem. The other problem is when it comes to the Large Igneous Province area, and trying to match it to the carbon output. Well, just the area alone is not a good proxy, right? Because you need to at least think about the thicknesses, the volume of basalt. But then, I mean, I've seen studies that show that different mantle plumes are mobilizing different amounts of carbon from the deep earth as well. So yeah, there's a bit more work to be done, but with the volumes, I guess you could do a better estimate of the volume of basalt from oceanic crust, because, well, most of them have not been really eroded. The continental outlines of some of these lips, you could, I know I have seen some schematics, at least, of people, trying to join the dots of Camp and even the Siberian traps. I was actually shocked for teaching the other day. I was showing the students, and we were comparing just Siberian traps, and then if you were to do the outline, it would actually cover half of Australia, the equivalent. So it was clearly a big event. But yeah, I'd love to hear what you think, if there are some low-hanging fruits to improve.
Yeah, it's just difficult with you. It's difficult to make the study. So that's why I don't want to be overcritically, but the uncertainties sometimes can be larger than the signal. And this is what I was experiencing as well with these kind of deep time reconstructions. And then it gets really tricky to carve out a conclusion if you are aware that your error bars are actually larger than your signal. So it will be only qualitative trends, and this is important to pave the direction for future research, but it's also has to be taken with a grain of salt, of course.
Yeah, of course. When your reconstructions change in a big way, it changes some of that. But we've analyzed different plate reconstruction options and scenarios, and most of the trends are still there. Like you say, it's the trends that are really important. And, I mean, I just present work that's like an incremental improvement over previous stuff of, just looking at a static map and drawing a line. So yeah, it's definitely incremental. But yeah, we need more data. We need better models. We need to quantify and minimize uncertainties, for sure.
That's essentially the conclusion of my talk that you just said, so I can maybe skip mine now.
No, look, I didn't want to preempt too much about the Rift stuff. There's a lot to discuss there. So we should probably take a few minutes break. People have a coffee and toilet break, and then Sasha can start at 11.